Now let's start the ResNet algorithm. I'll implement this algorithm using Keras. So first of all, over here, I'm importing all the required modules. And over here, you'll see, first of all, I'm importing all the layers from keras.layer. I'm importing input, add, dense, activation, zero padding layer. I'm importing all the layers which are required for this algorithm. And then I'm importing keras.models also for, by using this particular keras.model, we can create model and load models. And then I'm importing keras.preprocessing. This will help us, doing some preprocessing on image, right? Like this, I have imported all the required modules. Now, as I've told you, like ResNet is similar like other networks, but with the but in Resonant there is only one difference, that we are having identity connection between the layers. So as I've shown you in the very beginning, like this is an identity block, and identity connection simply means this input is traveling layer from this layer to layer, this layer to layer, and finally we are calculating f of x. And this identity connection simply means that we are adding this actual value of x. Using this skip connection, we are adding this actual value of x in function of x, f of x plus x. This is the final thing. And the main intuition behind Resonate, as I've just told you, like we algorithm will learn on the basis of function of x, and our target is to make function of x is equal to 0. Then only our output would be equal to input. Right. Now over here you'll see how many layers we have in this identity block. 3 layers. First layer, second layer, and third layer. Right. Now I'll show you the code of this identity block. So what I'm doing over here is, see, I am creating a function. Function name is identity block, right? And we are passing 3 parameters to it. I'll explain you all these features one by one, right? But just now, see, first of all, I will just give you an overview of this function, right? Identity block, then we'll go in deeper, right? So over here, you'll see first layer. This is the code for first layer. This is the code for second layer. And this is the code for third layer, right? And after this, all these 3 layers, what we are doing in a network, what we are doing in identity block, we are adding actual value of x with function of x, right? So after writing the code of 3 layers, over here you'll see I'm using add method, and what I'm adding x, and I'm adding x underscore shortcut. Now what is this? This x is which is traveling from, the x simply means which is traveling from layer by layer, right? And what is this x shortcut over here? See, if you'll see in the beginning of this function identity block, I'm having one variable with the name of x underscore shortcut. And what I'm storing in this x underscore shortcut, I'm storing the value of x in it. See, why I'm storing the value of x in it? Because the value of x will change as the x travels from layer to layer, right? So, and in our final over here, we want to add the actual x value with the function of x. So I'm storing the value of x in a separate variable, so that we can have a actual x value stored in some different variable, and later on over here we can add x. X is now, what is x over here? X is a variable which is carrying f of x, and this x underscore shortcut is a variable which is storing the actual value of x, and we are adding both of them, and finally we are applying the final activation function on it. And what is the activation function we are using in it? ReLU. See, why we use ReLU activation function? Because if when you use ReLU activation function, what ReLU does simply, ReLU simply means it will transform all the negative pixel values to 0, right? And this will help you in, this will help you, you'll not get the problem of vanishing gradients, because it will replace all the negative values with 0, right? So as you understand the basic structure of it, now let me explain you in depth what this code is actually doing. So till now we know that x shortcut is storing the actual value of x, which we will add this value later on in the final layer. And these 3 lines are the first layer code, these 3 lines are the second layer code, and these 2 lines belongs to the third layer code, right? And see, over here, okay, let me show you from the very beginning. So now the very first thing is we have three variable f1, f2 and f3, and the value which we are passing to this f1, f2 and f3 is in filters, this filters. Later on I'll tell you what is in it, but for temporarily let me explain you. See, this is the ResNet 50 architecture. The very ResNet 50 means we have 50 layers in our network. So when you count all these things, you will get 50 layers. See, first of all, we'll be having one layer which will be having filter size of 7 by 7, and we'll run 64 such filters with stride 2. This is the first layer of our ResNet 50 architecture. And after that, we have one MaxPool layer, and the window size in MaxPool is 3 by 3, and we are using stride 2, right? So after that, over here, if you'll see, oh, here and here, if you'll see, we have layers in the pair of three layers, right? So because why we are having the layers in the pair of three layers, because we are going to use identity block, and in identity block, how many layers we have in identity block? See, one, two, three, right? So over here in this layer architecture, we are using layer in the group of three. So the very first layer in the identity block, we will use a filter size of 1 by 1. And how many such filters we want? 64 filters. And in the same way, second layer of identity block will have a filter size of 3 by 3, and we are going to have 64 such filters. And the third layer of identity block will have a filter size of 1 by 1, and we are going to have 256 such filters, right? So this is the first block. Into 3 means this same structure will repeat 3 times. That means total we are going to have 9 number of layers. This grouping into 3, that means we'll have the same code thrice, right? Over here into 4 means we'll have this layer structure, this grouping of layer, how many times? 4 times. Into 6 means this these parameters of layers, we will be having these particular 3 layers how many times? 6 times in a network. So this is again 3 times, and if you'll add all these layers, you'll get total number of 15 layers, right? So as I just told you, just remember this: 1 by 1, first layer will have 1 by 1 filter size, second layer will have 3 by 3 filter size, and third layer again will have 1 by 1 filter size. And the number of filters in first 2 layers are same, and in third layer we are going to have 256 filters, right? So this filter is that basically. So now what we can say, that in F1, we can say that in F1, what value will go in what F1? 64. And in F2, which value will go in F2? This 64. And which value will go in F3? This 256, right? So why we are not providing values directly from here? See, we are using this filter. So this filter value, later on we have mentioned like how to assign values to it, but for your understanding, I have written over here that F1 will have 64 layers, F1 will have 64 filters of size 1 by 1, F2 will have 64 filters of size 3 by 3, and F3 will have 256 filters of size 1 by 1. Clear? And this x shortcut variable is again clear to you. This variable is used to store the actual value of x, because this x value will change when we use this x value in our architecture. So now the task is to write a first layer. See, what we are doing is, over here if you'll see x in x over here, x over here, x over here. See, what we are doing is we are updating the value of x. We are not using separate variable for every line of code. So what we are using, we are updating x value in every line of code. So the very first thing is, over here in x variable, what I'm storing is I'm creating a con2d layer, right? Convolutional layer. And this convolutional layer will have how many filters? Filters F1. And F1 having common filter, 64 filter. Kernel sizes 1 by 1, as I've just shown you. Filter sizes 1 by 1. Over here the value is 64. Over here kernel size is 1 by 1, and stride is 1 again. See, I have used padding valid and padding same in this whole code. So if you are not aware about what is padding same and padding valid, so in the comment section, I have added a link which will explain you about this padding same and padding valid with proper examples so that you will have a proper understanding why I'm using this padding valid and padding same, right? So I'm using padding valid over here, and this is the input which we are providing to it. And what is this? This is the value from here, the actual input value, right? So once we have applied these many filters, see in this ResNet network, in second, after every convolutional layer, we perform batch normalization. So over here we are performing batch normalization, and axis 3 simply means we want to perform batch normalization on output channels, right? So how many output channels we have right now? 3 output channels, RGB, colored image, right? So we are performing batch normalization on axis 3. Axis 0 is rows and axis 1 is column. So axis, in the same way, this axis 3 means the this output channels. And what is the input to this? Again, X is the input to this layer. And which X is this? X from the previous layer. The output of previous layer will become the input of next layer. Again, we are having X variable, and then we are performing activation function on it, and ReLU we are using. As I've explained you, ReLU will help you out in, you will not have a problem of vanishing gradients, because if you'll use TANH or other activation function, they will give you a problem of vanishing gradients. ReLU will replace all the negative values with 0, and over here we are using ReLU activation function. So this is the task of first layer. Now let's talk about the second layer. So what are the dimensions, what are the parameters second layer is having? So filter size is 3 by 3, and how many filters? 64 filters. Let's see how to write it. So creating convolutional layer again. So filters, how many filters we want to have, which are stored in F2, and what we have in F2? 64, right? Kernel sizes F comma F. F simply means from here, filter size is F. See, in our whole this layer structure, you can even write 3 comma 3 over here. So the value of F is later on we are getting this value of F, but for your understanding, just understand over here the kernel size is 3 comma 3, and this F later on, this F will provide the value of 3. So right now just assume 3 comma 3 over here. Stride is again 1, and padding, as I've told you, go through the other tutorial which I have shared, and you'll get to know what is it. And then again we are doing batch normalization, and then again we are performing activation ReLU function, right? So this is the code of second layer. Now let's talk about third layer. Again in third layer, let me show you the code for third layer. Third layer will have filter size of 1 by 1, and how many such filters we want? 256 such filters. So let's see how it is working. So we have created a convolutional layer. Number of filters is equal to F3, and in F3, what is the value in F3? 256, right? And kernel size is 1 by 1, and stride is 1 by 1, and again we are doing batch normalization. See, over here the important thing is to note. So see, in the very first two layers, we are, after batch normalization, we are performing activation function. But in third layer, after batch normalization, we are not performing ReLU function. Before performing ReLU activation function, we are adding the actual value of X, which is stored in X shortcut, and the f of X, the output, which is stored in this X, we are adding them, right? So this is the, after adding this X into f of X, we are applying the activation function, ReLU function, and then we are returning a X, right? So this is how our identity block works. So if you remember, you can see over here. So after third layer, before performing this activation function, we are adding f of X plus X, and then we are performing the activation function of last layer. So this is what identity block is, right? So now I hope this is clear. Now let's move further. There are other aspects which we need to take care while creating this identity block or while using this identity block. Now always remember, see, if the input size of image and the output size of image is same, then we can use identity block. So what I mean to say is the input which we are giving to our network is, let's suppose the input is 224 into 224 into 3. And while this input is moving from layer to layer, and after completing the whole task, if the output size of if the output volume is 224 into 224 into 3, input is again same and output is same, means the input size of the image and the output size of the image is same, then we can add the actual x value into f of x, right? Means identity block will work when the input size of the image and the output size of that particular block is same, then only we can add this x into f of x. But let's suppose if the size is different. Let's assume the input which we are giving to our network is 56 into 56 into 64. This input is first moved to this layer, and from this layer to this layer, and after this layer to this layer. And let's suppose after moving after this input moved from few layers, the output size is 28 into 28 into 128. Let's assume this. Now the input size of image is different and the output size of image is different, right? So in this case, we can't use this identity block, right? That simply means we cannot add this x value into f of x. Why? Because the input size of the image and the output size of the image is different. So what to do now? So if you'll see over here, if you'll observe, I have added one layer in this shortcut path. Right. So this is basically called convolutional block. See, convolutional block will help us to add the input with this output when the input and the output image size is different. So you'll see we have rest of the task is similar. These three layers, and this is the shortcut connection. This is how identity block looks like. But there is only one difference. See, we have one more convolutional layer over here. Let me show you the identity block again. See, in identity block, we don't have any layer over here, right? Because the input size and the output size of the image is same. But over here, the input size and output size is different, and this is a convolutional block. Convolutional block and identity block is similar. There is only one difference. Like in convolutional block, we have one more convolutional layer in between the shortcut connection, and the task of this convolutional layer is to make the size of this input equal to the size volume of this output. Right? Clear? Why we are using this convolution layer in between shortcut path? Because we want to make the size of this input equal to the size of the output, so that we can add this input to the output. Now, how this convolutional layer will, make the size of this 56 into 56 into 64 to a 28 into 28 into 128. So there are two options for matching the output size. Either we can pad the input volume, or we can perform the one by one convolution. Don't worry if you don't understand, I'll explain you how to do it. So I'll show you, I will, resize this image to this size by using the second method, by performing one by one convolution. Let me show you how to do that. So this is the input size and this is the output side, and what I've just told you, like I'll use one by one convolutional over here to make this size equal into this size. And if you're familiar with this formula, n plus 2p minus f by s plus 1 into n plus 2p minus f by s plus 1. So CNN is using this formula to, CNN works on this formula. So n is the image size. So what is the image size over here? 56 minus. So this one, okay, over here we'll not use plus 2p. The formula over here is n minus f by s plus 1. Sorry, there is a mistake. There is no, the formula is n minus f by s plus 1, right? Because we are not using padding over here. So this p stands for padding. So n is 56 over here and minus 1, this f means filter size, and what I've told you is we'll use one by one filter size. So the size of filter is 1 and stride is 2 plus 1. So when you solve this, you'll get 28. In the same way, in this side also you'll get 28. So the image which is of 56 into 56, when we pass this image from this convolutional layer, this convolutional layer is performing a one by one convolutional, and by using this formula our image size became 28 into 28. Now the size of this and the size of this is same. Now we can add it. So always remember. Now let me show you the code of this particular thing. Right. See, identity block and convolutional block is doing same thing. The only thing is both identity block and convolutional block are responsible to add the actual x value into a function of x. The only difference is we'll use identity block when the input size of the image and the output size of the image is same, and will add x into f of x by using convolutional block when the input size of the image is different from the output size of the image. Now let me show you this convolutional block with the help of coding, as I've just shown you how to use identity block. So this is the convolutional block. Again we have a function convolutional block. Again, these are the required parameters. F1, F2 and F3 will get the values of filters. Which filters I'm talking about? Means how many filters over here, if you'll see over here. So in the very first block, we have filter size of 64, F1 we have 64, F2 have 64, and F3 have 256. And if I talk about this block, F1 will have 128, F2 will again have 128 filters, and F3 will have 512. And if I talk about this block, F1 will have 256 filters, F2 will have 256 filters, and F3 is 1024. So these are F1, F2, F3, right? So over here, so again x shortcut is storing the actual value of x, because later on the value of x will change and we want to add the actual value of x at the last step, so we are storing it in a separate variable. So again see, first layer, second layer and third layer. Task is again same, the whole code is similar. See, the only difference will come over here. After in identity block, what we are doing after third layer, we are directly performing this code, right? We are adding x with x shortcut. But over here, we have a layer in between. Remember this layer, right? Before adding, we are we have written the code of first layer, then we have written the code of second layer, then we have a code of third layer, right? So before applying, before adding this with this, there is one more layer. So this is that particular layer, right? So this is that particular layer, and the thing to remember over here is which technique we are using over here. We are using one by one convolutional. So this is a filter size one by one convolutional layer over here, and stride S is storing 2. Stride is 2 over here, right? Stride is 2. So after doing that, we are adding x with the function of x, and then we are applying the activation function. I hope the convolutional block and the identity block code is clear now. Now let's start with the ResNet algorithm. See, till now we hadn't created ResNet. We are just preparing the two functions which are required while creating ResNet: identity block and convolutional block. Convolutional block will pass the input to the output when the input and output size volume is different, and identity block will pass the input when input size and output volume is similar. So this is the ResNet 50 model. So the very first thing is of this ResNet model is we will perform 64 filters of size 7 by 7, and this slash 2 simply means stride 2.